for coming. So I realize the background may be somewhat different, so I won't assume too much. I will assume something, and it is in your best interest to ask questions whenever there is something you don't understand. So please do stop me at any time and ask questions. Sometimes I'll have to be vague, sometimes I'll have to skip some facts, but hopefully some of the important ideas will appear. So this is going to be about abelian varieties and integrable systems. So can you read this from back there in the last rows? Yeah, okay. So the plan is roughly as follows. So I'll first talk about what abelian varieties are. And there are two ways we can think of them. We can think of them algebraically. And I'm somehow implicitly assuming that many of you may be more inclined towards algebra than towards analysis. So this may be a more natural way for you to think. Or you can think of them analytically. And I'll try to present both approaches with some details, but not all details. Then we'll talk about Riemann surfaces and the Jacobians, which you can again think of algebraically or analytically. Okay, and then somehow in here there will also be a discussion of theta functions for both Riemann surfaces and for abelian varieties in more generality. Then at some point there will have to be integrable systems that will appear. So what I will discuss the geometry of Kumho varieties, and from here we will see some partial differential equations for the theta function. And then somehow I will have to step back and give a completely independent sort of introduction to how you might want to think about integrable systems. And the goal will be characterizing Jacobians by integrable systems, by certain partial differential equations, and this will somehow heavily use the machinery of integrable systems that we will develop by then. I will probably spend quite a bit of time introducing everything in all the ways I would like to introduce it, because there are different ways and approaches in which you can look at it. The difficulty in the theory comes from the fact that there are many different pieces that have to come together for the results to be proven, and some of these pieces are much easier to state algebraically, and somehow if you state them in the language of algebraic geometry, you have a good view of what happens geometrically. But somehow there is characterization that I'll eventually somehow tell you about. It will be a geometric statement that hopefully I'll get to state in the end of today or early tomorrow, but the proof will be completely analytic. And there is no algebraic proof known to man so far, which means we'll have to develop some analysis. And at some points developing this analysis, it will be analysis. It will not be analysis as just another name for some algebraic manipulations. There will be something significantly and crucially analytical. So there will be functions with essential singularities, infinite formal power series, and things like that, which I don't really know how to phrase algebraically. So that's roughly the plan. And there'll be some background. I'll assume some complex analysis, some basic algebraic geometry knowledge of what a divisor is, what a line bundle is, and so on. Some things I'll just state as facts. I won't prove them. You should still ask me if there is something you don't understand. Some statements I'll write as exercises. This does not mean you should do them necessarily, but it's something that I think is a good example to think about to make sure you understand what is going on. and I'll be happy to discuss them. Also, as you know, I'm here and I'm happy to answer your questions at any time outside of lectures as well. So let's start with definitions. So I'll start by talking about what abelian varieties are. So the simplest, so genus 1, so genus or dimension, depending on how you look at things, 1. So here what we would like to talk about is elliptic curves. So what is an elliptic curve? So elliptic curve, I mean, if you're in algebraic geometry, just draw that and you say 1, and you mean an elliptic curve. Or if you think about this as Riemann surfaces of genus 1, and then you probably draw a picture that looks like that. But now let's try to be sort of projective geometers. So if we have an elliptic curve, I would like to claim it's a projective variety. So I would like to claim that an elliptic curve can be embedded in a projective space, right? So how do you do that? So to get an embedding in a projective space, presumably you would need some very ample line bundle. So it would be helpful to have any line bundle. So what is a line bundle on an elliptic curve? So line bundle, so sort of a point is a line bundle. I mean, is means, I mean, there is some kind of equivalence between codimension 1 subvarieties and line bundles on an elliptic curve. Right, so if you have an elliptic curve, a point on it defines a line bundle on it, which somehow is the usual thing, that the subvariety of codimension 1 is a line bundle. Okay? So how do we want to think of an elliptic curve? Well, we can think of it this way or that way, but there is another way to think of an elliptic curve. And this is, you can think of it as a rectangle with a gluon. So this means you are trying to think of an elliptic curve as a quotient of c by z. So if this were 1 and if this were 2, the other thing you want the quotient by is z 2. So what do I mean by that? This means I consider the set of points, you know, so this set is a set of points n plus m2, where n and m are integers, and that's a subset of C, right? Moreover, it's an additive subgroup of C, and I can take a quotient of C by this group. And what I get is best depicted by drawing a parallelogram with sides 1 and 2 and telling you to identify, because that's what the quotient looks like. And this is an elliptic curve in some other way. So let's try to think about which of the three pictures of the elliptic curve we might like the most. So this means let's try to generalize what we should think of. Generalizations to higher genus. So, well, I mean, if you're drawing this picture, nothing stops you from drawing this picture with a G. So this is to say you have a Riemann surface of a genus G. So you say you draw something like that, and you say there are a bunch of holes. So there are G holes. Okay. So this is, of course, a Riemann surface of genus G. Okay. Well, a point is still a line bundle. On the Riemann surface. And to be perfectly honest, I have to admit that this is actually an ample line bundle, right? Because if you take a very high multiple of this point, it becomes very, very positive. We'll have very many sections by the Riemann-Roch theorem, which I will sort of assume for curves. Okay? So technically what I'm trying to say is that divisors on x, where x is any variety, and I'm loose, so let's say nice, smooth, and so on, correspond to line bundles on x. So what's a divisor? So these are the subvarieties of x of complex codimension 1. So in particular, if you have a Riemann surface, a subvariety of a complex codimension 1 means just a finite collection of points. So a point defines a line bundle on X. So any line bundle on a Riemann surface. Oh, sorry, this was not part of this. Any line bundle on a Riemann surface corresponds to a linear combination Ni Pi for Pi line, in the Riemann surface, and Ni being integers. Okay, that's what I really mean. And what I wanted to emphasize here is that if I take the line bundle to be just P for any point P, this is an ample line bundle, which is to say that if I take, claim, fact, so let me call fact something that I'll ask you to accept for granted, okay? So fact is NP is ample on a Riemann surface for any n sufficiently large. So for any Riemann surface X, for any point P on X, a large enough multiple of this point is going to be ample. Okay? So that's a corollary of Riemann-Roch, if you wish. Okay, so that's what I mean here. And this is one way to generalize an idea of an elliptic curve. Of course, this is fine here, but now what do we do here? So here, notice if we want to draw this picture, well, there aren't so many different interesting subgroups of C. If we want to take a lattice in C and we want it to be nice, there are not so many choices. So there are certainly not many dimensions. So idea of an abelian variety is as follows. I want to take C to the G now, quotient by Z to the G plus Z to the G times Tor, for some Tor being a G by G complex matrix. Okay. So in genus 1, a 1 by 1 complex matrix is just a complex number. So this is okay. But notice that the real question to ask here is, in dimension 1, an elliptic curve is certainly an algebraic projective variety. In higher dimension, you can ask a question. When is this a projective variety? Okay. And then another question you can ask is how does this relate to Riemann surfaces of genus G? And the last question you can ask is, what is the moduli of such objects? Okay. So essentially, for this question, you would need to know when such a quotient admits an ample line bundle. For this question, you would somehow need to have a construction that relates these two. In fact, there is a construction of a Jacobian of a Riemann surface that goes from here to here, which I'll describe shortly. And for this, we'll discuss what we mean by moduli and what are the interesting questions. Okay? So this is the motivation. And for considering abelian varieties, this is sort of a natural generalization of a notion of an elliptic curve. So far, I haven't given any formal definitions, but let me say what the goal is. So we note that to go from here to here, there is a construction of a Jacobian. So Jacobian of a Riemann surface is an abelian variety. So it's a quotient of such a kind, which is actually a projective algebraic variety. And the question that is somehow the main point of discussion here is the following question, also known as Schottky or Riemann-Schottky, depending on your preference, problem. And this is a question of which abelian varieties are Jacobians of Riemann surfaces. And the goal for the talks, give two answers to this question. Okay. One of the answers I will be able to state completely geometrically. The other one I'll need to write some kind of formula for. Okay. So let me maybe explain what happens here. So there is a notion of Riemann surfaces of genus G, which hopefully we all know. And then there is a notion of high dimensional abelian varieties. All of this, by the way, is over the field of complex numbers. I mean, everything is complex, so I'll never mention that. Okay? And given the Riemann surface of genus G, you can correspond to it as Jacobian, which is an abelian variety. And in fact, the Jacobian will determine the Riemann surface uniquely. So if you know the abelian variety as a Jacobian, you'll know what the curve is, what the Riemann surface is. And then you can ask which abelian varieties actually come up as Jacobians of curves. And the answer is not all of them do in higher dimensions. And then you can ask which ones do. Okay? I'll formulate all of this precisely very quickly, but this was just motivation. Right? So I allowed myself some minutes to motivate the question. And notice in genus 1, when we're talking about elliptic curves, somehow we have all internalized, perhaps at some point, or maybe we can think about it and prove it, that somehow this picture of an elliptic curve and this picture of an elliptic curve are completely equivalent. That you can go from one to the other without so much trouble. That if you know how to write an elliptic curve in this way, you also sort of know it as a Riemann surface of genus 1. On the other hand, if you have a Riemann surface of genus 1, you can look at it this way. And there is a one-to-one correspondence in the sense that somehow the moduli of Riemann surfaces of genus 1 and the moduli of abelian varieties of dimension 1 is really the same space. And this continues in dimensions 2 and 3. That's also essentially the case, but then it's no longer the case. And that's a very interesting, I think, question to try to relate it. So if we look at it, we see that here this is a very geometric picture of something. So this is a very geometric object. Here I'm taking a quotient by something, so it's a bit more analytic to start with. In fact, number theory enters here very quickly, and there is some analytic number theoretic questions. And that's why this question somehow relates some algebra geometric notions and some more number theoretic or analytic things. And approaches to it somehow usually combine insights from both viewpoints. Okay, so this was an introduction, sort of a motivation, if you wish. Now I'll start, in earnest defining things and saying precise things. But is there sort of a question about what the general goal is? We'll try to understand which abelian varieties are Jacobians. That's somehow the question. I'll define abelian variety properly now. I'll define a Jacobian properly, and so on. Questions? Okay. The integrable systems will not appear today for sure, and somewhat unlikely to appear tomorrow, depending on how fast we go. They will make their entrance in a grand way when the time comes. Okay. So, definition. An abelian variety, complex. So I'll stop saying complex because everything is complex. An abelian variety of dimension G is a projective, complex, G-dimensional with the structure of a group. Let's call an abelian variety A, with a structure of a group on its points. So what I mean is that there is a map from A cross A to A, which is the group law, such that the group structure is compatible with the holomorphic structure you have, with the algebraic structure you have, such that the map A cross A to A, which is the composition, and the map A to A, which is, x goes to x inverse, so this is x, y goes to x, y, such that these two maps are algebraic, if you wish. Okay? So this is the definition, right? Now, given this definition, if I wanted to ask you, please give me an abelian variety of dimension g, what will you do? Well, you'll have to scratch your head and you'll have to think, because this is somehow very abstract. It's very non-concrete, right? So let me give another definition, which is the following. A complex g-dimensional torus is a quotient A, and I know it's a bad idea to denote at the same letter, but never mind, c to the g quotient by some lambda, where lambda is an abelian subgroup, well, it's a subgroup of c to the g on the addition lambda. So a subgroup means, well, let me say that lambda is of maximal rank, so lambda is isomorphic to z to the 2g, and if you take lambda and tensor it with r over z, you get all of c to the g. So let me explain the last condition, because I just wrote that formula and I should probably explain what this really means. So this essentially means I want to take a lattice. I mean, it's a lattice that's generated by 2g basis vectors. And this condition says that these 2g basis vectors are an r basis of c to the g. I mean, c to the g is the same as r to the 2g, of course. And what I'm saying is that the 2g basis vectors that I have for this lattice have to be an r basis of this space. So they sort of have to span everything. So in the example of genus 1, my Tor really should not lie on the real line. That would be bad. Okay, that's prohibited. In general, this is a more complicated condition, saying that a generator set for this lattice spans all of r to the 2g. Why do I want this? Well, a complex torus is a complex variety. A complex torus is a complex variety, complex manifold, I guess I should say, with a group structure, right? Because I can certainly add points here. I just take 2 points in here and I add them, their preimages on c to the g, and this is well defined still up to the lattice. So then you can ask, maybe a complex torus could give me an example of an abelian variety. And this is in fact true. So fact, all abelian varieties are complex tori. So fact, all abelian varieties are complex tori. So I won't prove this, but let me explain what this says. This says the following, that if you have a projective variety that's a group, A, this group automatically has to be a commutative group. B, that this will imply then that if you take this projective variety and take its universal cover, it's going to be c to the g. once you know that the universal cover is C to the G, it's very easy to verify that the variety will have to have this shape, this form, this representation, whatever you want. But this is something that you need to prove. So if you may want to consider it an exercise, but I don't advise you doing this. I mean, this would require some knowledge that goes outside. Okay, so you don't have to believe this. We won't really use it because, I mean, in a second I'll just say which complex tori are abelian varieties, and you are free to take this as a definition of an abelian variety. But this is somehow the general framework that it might be helpful to have in mind. So the question, of course, is which complex tori are abelian varieties. So what is really the question here? Of course, a complex torus, it's a holomorphic manifold. It's a complex manifold. And of course, it has a group structure, which is nice and holomorphic, and there is no problem. But the real question is whether a complex torus is a projective algebraic variety. Okay. So that's the question you could try to address. So let's try to think about genus 1. Well, in genus 1, whenever you have a complex torus, so here I didn't fix this in genus 1, in dimension 1, this does not have to be generated by 1 and tau. It could be generated by any two vectors. But still, a point is going to be an ample line bundle no matter what you do. So any one-dimensional complex torus is an abelian variety. There is no question. And this is somehow very important, I think, to understand that this distinction only happens in higher genera, that not all complex tori are abelian varieties. There is some extra data you need to know. So what will this extra data be? So this is sort of a result due to Riemann. So sort of it's a theorem due to Riemann. This is called Riemann's bilinear, whatever. But this is Riemann's theorem that a torus C to the G, and now I'll write it the way I was writing it up there. So I'll write it as Z to the G plus Z to the G tor is projective, is a projective variety if and only if the matrix tor is symmetric. So this is tor is symmetric, and the imaginary part of the matrix tor is positive definite. Okay, so that's the result. So what I would like to remark here is that any complex torus which will in general look like that is bar holomorphic to C to the G over Z to the G plus Z to the G tor or some tor. So let me first explain the remark, then I'll make some comments to improve the believability of the theorem. So if you have a lattice that's generated by two G vectors, let's choose the first G vector. Let's choose G vectors, G generators of the lattice. They're going to be some linearly independent vectors in C to the G. Let's just act by an element of the general linear group of C to the G, and let's map them to the unit vectors in the first G dimensions. Okay? Once you do that, the remaining G vectors will form some kind of matrix. That's the matrix we are left with. Okay? So this is clear. There is a way to state this for a general matrix. You'll have to write this as a G by 2 G matrix and write something, but it amounts to just that if you do your linear algebra carefully, so I don't want to bother with that anyway. Okay, so now let's get to the theorem. So there are two statements here. First statement is that if tau is indeed a symmetric, positive, definite imaginary part matrix, then this thing is an abelian variety, which is to say that it has an embedding in projective space, which is to say it admits an ample line bundle. Okay, so this is a statement that if the imaginary part is positive, definite, and the matrix is symmetric, then there exists an ample line bundle. I will actually prove, but not now. Will be proven by constructing this bundle explicitly. By an explicit analytic construction. Which is to say, given such a thing, I will just write down a formula that will define for you a line bundle explicitly. Since we're now doing an algebraic introduction, I'll postpone this formula and I'll ask you to trust me. Now the other direction, so if there exists an ample line bundle, then tau has to be symmetric, and the imaginary part of tau is greater than 0, I would like to give some indication of here. It wouldn't be a complete proof, but it would be sufficient indication so that if you have some familiarity with complex projective geometry, you should be able to reconstruct the proof. And if not, please feel free to ask me for more details outside of the lecture room. So what happens here? So what is a... So let me say that given an ample line bundle, so this is a general, an ample line bundle L on a projective variety X, we have its Chern class. We have the first Chern class of L, which somehow, I mean, determines much all of the numeric data about L, right? So this is a Chern class. So it's a two homology. It's a class on the second homology of X, right? With integral coefficients, because this is actually a line bundle, right? It's an actual line bundle. It's not a Q line bundle or something strange. It's just an honest line bundle. Moreover, it's a Chern class of a line bundle, so it's sort of nicely. It has to be in H11. So if you write the Hodge decomposition, it will be in here. Okay, and the fact that it's ample means something about positivity. So I'll write positive. Okay. Okay. So this is something that you'll sort of have to accept because I won't be able to go into a complete discussion. But in any case, so what we should think of is that the Chern class of a line bundle is a two-form it's a two-form, which is integral and which is sufficiently positive and is in the right piece of the Hodge decomposition. Now, on a complex torus, C to the G quotient by this thing, well, you can describe homology. So you notice that if you take H1 0, so this is holomorphic one forms on such an object. Well, what are the holomorphic one forms? You can lift them all to C to the G, right? And then you just think about it, and you see that the space you get is just C to the G, because this is just generated by dz1 ... dzg linear span. So, I mean, if you wish, you can study a product of a bunch of elliptic curves, convince yourself that's the case for that, and then this has to be invariant sufficiently, especially if I put the z in at some point. Okay, and if you want to look at H11 of AC, this will be a product of H10 and H01 of AC. So this is just a, so this will look like, so the basis will be given by dzi tensor dzj bar. Okay, and the space we get is C to the G. C to the G. Okay. So this means that if we have, at the moment we have a line bundle, we have an object in here, which is integral. Okay, so given such L, we get a bilinear pairing taking a lattice by which we have a quotient in this lattice, tensor the lattice to Z in fact. What you do is, suppose you take vectors u and v in the lattice, what you want to send them to is you want to integrate the C1 of L, right, over the span, R span of u and v in A. Okay. So this unfortunately exceeds my ability to draw, because I'm supposed to be drawing something four-dimensional. But what happens is the following. So you have two lattice vectors. So I'll draw somehow a picture which is misleading, but somehow gives you some idea. So here is my lattice. So let's draw a lattice. So and suppose I have two vectors in the lattice, this one and this one, right? And of course, if I want to extend them, so they have a linear span. But this linear span, since they're lattice vectors, it will close up. So if I wanted to project from here to one domain, so if I wanted to look at the picture of projection, it will just cover, in one-dimensional case, it will cover everything. In higher dimensions, you should think that you have, a big multi-dimensional torus inside which you'll just have a couple of vectors that will somehow have a span, right? Of course, this is a real picture. You should have a complex picture. So this span, anyway, it's a real two-dimensional thing. This is a 1-1 form. You integrate to get a number. Okay, and you notice that since the C1 of L has to have integer coefficients in H2, this is to say that this map, in fact, ends up in Z. Okay. And this then you need to classify odd, and it's odd, of course. Classify odd bilinear forms, bilinear integral valued forms on Z to the 2G. Cross Z to the 2G, right? Because this is isomorphic to Z to the 2G, and you just have a map to Z, right? And there is a fact that they all look like the following. I'll write it in block form. So this is in G by G blocks. And two of the blocks are 0. And here you have some numbers, d1 dot 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 dg 0 0. Here you'll have minus d1 minus dg 0 0. They all look like means they are all isomorphic to this if you choose the basis properly for some d1 dividing d2 dividing d3 integers. And then from this, I claim you can see that the imaginary part has to be positive definite. That you can see already from here. And then you see the symmetry also, because this has to be appropriately symmetric. Okay. By the way, the reason I was writing this classification here is the following: is definition given an ample bundle, line bundle, L on such an abelian variety A, D1 dot 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 Dj, the string of numbers is called its type. Okay, and this is an invariant of a line bundle, so it's a numerical invariant of a line bundle. Okay, so this was an incomplete proof of the fact. This was an indication of how you would see that if you have a complex torus that is an abelian variety, that's a projective variety, then its period matrix has to be symmetric with positive definite imaginary part. Does this make some sense? I mean, I'm not claiming it's a complete proof, but does this start to seem somewhat believable in one direction? Okay. So you have to work with this a bit more. You have to understand more clearly and more rigorously the relationship between this and this, but that's how it roughly works. Okay. So that's one fact. And again, the other implication, which algebraically would have to work to prove, or somehow you would have to understand what happens here well enough to construction things, I'll just write down the formula eventually. Okay. So thus, any abelian variety is biholomorphic and also sort of isomorphic as an algebraic variety. To a complex torus C to the G quotient Z to the G plus Z to the G tau for some tau which is symmetric and the imaginary part of tau is positive definite. Let us denote for future use this abelian variety by A sub tau to indicate that it corresponds to tau. Okay? I didn't claim just uniqueness of tau. I just said that any abelian variety can be written down in such a form, maybe for many different taus. Okay. So an abelian variety is a projective variety, so there is an ample bundle in it. So the definition is just a word. A polarization on an abelian variety A is a choice, is an ample line bundle L on A. So just a polarization is a name for an ample bundle on A. So by the way, if you didn't like this or didn't if I didn't explain it very carefully, it doesn't matter. As long as you believe this, I'm happy. We don't really need to understand this part for what follows. Okay? So a polarization is just an ample line bundle on A. So just a name. Another definition is we somehow need to distinguish different polarizations, and in general there are many, of course. You can take a multiple of an ample line bundle, but we know that any polarization gives you something like that, gives a set of numbers d1, dj. So definition, a polarization is called principal if the dimension of the space of sections of it is 1. So essentially, if there is only one section up to multiplication by a constant. Okay? So equivalently, this is to say, if the type of polarization, according to that definition, is 1, 1, 1, and so on, with all ones. Okay. That's a fact that I would also like to skip. Okay. So this is a definition of what a principally polarized abelian variety is. Why do we care about polarizations? Well, there are many different reasons. So let us try to understand somehow geometry of abelian varieties. So if you have an abelian variety, you can study what line bundles does it have in general. So let pick of A be, all line bundles on A up to linear equivalence. Okay. Similarly, you can have pick node of A, which will be line bundles on A that are numerically 0 essentially, right? And there is a formula that I have to write in the correct order, yes, that are numerically equivalent to 0. So let's look at the set of line bundles that are, let's look at this set. If I have two line bundles, we can take the tensor product. This will define a group structure, which of course will be a nice abelian group structure on the set of line bundles. The only problem is that, you cannot really take the inverse so easily. In general, unless you try to, but let's be careful. So what I want to say, you have to think. So on vector bundles, you cannot forget what I said. So let's take pick node of A. So definition: the dual abelian variety A hat is by definition pick node of A. So I claim that this is an abelian variety. So the fact that it's projective variety hopefully would be a general fact about the Picard of anything. So it's an algebraic object, so that should be okay. If you want to take the 0 is certainly in there, that's just a 0, a trivial line bundle. The inverse is just you take the inverse of a line bundle, so you take the inverse of the transition functions. The tensor product is there, and that's in here. So there is a theorem due to Appel-Gumpert, which says that if you want to study all line bundles on an abelian variety, then they're all classified by their numerical properties. You recall that C1 of a line bundle was in here, so this is a shorthand. Maybe I shouldn't use it. So this is H11 AC intersect H2 AZ. So this is where the Chern classes of line bundles should end up in. Okay, and if it's not ample, it doesn't have the positive. So this is a theorem that says that this is an exact sequence, which is to say that if you want to know something about the line bundle in an abelian variety, there is a degree 0 piece here, and there is a numerical piece here. Okay, so given a polarization, given any line bundle, L on an abelian variety A and given a point A in the abelian variety, we can define the translate of this line bundle by L. So this is the pullback of L under the map taking the abelian variety to itself, which just takes any point x and adds a to it. Right? That's an automorphism of the abelian variety, just shift. So you can pull back a line bundle. Okay. For any L, we can then consider, for any L and any A, we can consider the pullback of this line bundle tensor the inverse of the line bundle. So minus L. So what happens here? Of course, if you translate, you didn't do anything at all to this space. Remember, this was generated by DZIs, which certainly are invariant under translation. This couldn't care less. So this thing will be in peak node. Okay? So thus, any line bundle L gives a map from the abelian variety to its dual, to the dual recall is peak node, by taking any point A to the translate of this fixed line bundle L by A minus L. Minus means the same as here. I'm just using the additive notation for line bundles here and multiplicative here. I want to use additive notation from now on. So additive notation for line bundles. Okay. And a principal polarization is in fact equivalent to an isomorphism A and A hat. So this is a fact. So what I'm claiming is that if you have a principal polarization, so if L is a bundle of a principal polarization, this map will give you an isomorphism of the abelian variety and its dual. Somehow you're supposed to be able to see that by constructing the inverse in that case. And for a principal polarization, you'll be do that. And if you have such an isomorphism of this kind, then this is a principal polarization. Okay? So for a principally polarized abelian variety, you can identify the abelian variety with its dual, which will somehow be useful for many of the things we do, that we'll be able to think of a point on an abelian variety either as a point or as a line bundle. Notice this is something very nice, because in genus, in dimension 1 for elliptic curves, we in fact discussed that points are the same as divisors, right? And this somehow allows us to think of a point on an abelian variety in any dimension as a divisor, even though, of course, the point is codimension G. And notice this is not the same as identifying a point with a divisor in genus 0, because in genus 0, a point was a divisor of degree 1. This is a divisor of degree 0, right? I mean, we're only talking with peak knot, about peak knot. Okay. What else did I want to say? So I wanted to study then homomorphisms of abelian varieties. So homomorphism just means you preserve the group structure. So given a homomorphism P from one abelian variety to another, the kernel of P, right? The kernel, I mean, it's a subset here. There is a point here called 0, which is the image of 0 and c to the g, if you wish, is a subgroup of A1. Okay? So now let's try to understand what subgroups does an abelian variety have in general. So what subgroups does an elliptic curve have? Well, you just take a point, you take another point, and you just take a subgroup. If you're talking about a homomorphism that's a nice algebraic map, the kernel should be a nice algebraic subvariety. That's the inverse image of 0. So this means it's a subgroup that is an algebraic subvariety. So in genus 0 in particular, you can only have finite subgroups or everything, because the abelian variety is one-dimensional. If you don't have something finite, there's a risky closure of that would have to be everything. That's impossible. So for a very general abelian variety, A, I want to claim a proposition. The only subgroups of A are finite sets. Okay. So I want to say that an abelian variety generically does not have an abelian subvariety. The only algebraic subgroups. Subgroups of A that are algebraic varieties okay. This is to say that a very general A has no abelian subvarieties. Because you see, if you have a kernel, I mean it's a subgroup, so it's a group in particular, so it has to be an algebraic variety for the structure of a group, so it's an abelian subvariety. So let me try to explain what this happened, why this is the case. So the formal proof, you need to think a little bit. So proof. So what does it mean for A to contain an elliptic curve as a subgroup? What would we need? We need to have, this elliptic curve. So I cannot draw the picture again. So imagine you have a large dimensional torus inside which you have an elliptic curve. So what does it mean? So an elliptic curve is generated by two elements, by two vectors. So we need to have vectors v1 and v2 in the lattice here, such that the vector v2 is equal to some constant c times v1 for some c being a complex number, right? But this vector sign here, so the vectors in c to the g, and we have a discrete subgroup of c to the g. So we have, so here is v1, and here is, I don't know how to draw it, here is 0. So here is c v1. So this is the c-span of the vector v1. Of course, generically, no other vector of the lattice is going to lie in there, right? Morphism group of A, so the group of self-maps of A which preserves the group structure, is equal to Z. So this corresponds to maps Z goes to NZ for n being an integer. Right? So the proof is as follows. The kernel has to be a finite set of points. So the map has to be onto. So the kernel has to be, I claim, of the form just finite, the points of order n. And that's what you get. Okay? So as an exercise for T is the following. So compute the endomorphism group of an abelian variety across itself for A very general. Notice that it doesn't have to be the same because this only worked for a very general abelian variety, and the product of an abelian variety with itself really doesn't have to be a very general in this sense. Okay. So I think we should break for 1 hour now. I'm happy to answer your questions privately during this time, and we'll resume in an hour. Thank you.